Okay, let's begin. So, no quiz today. Oh, I love you. Good. Here's what's going to happen. So I did write 2 quizzes. I wasn't kidding about that. But I'm just not going to give you as a real quiz.
Yeah,
I'm going to post them online. I'll post the quizzes online, and I'll post the answers to the quizzes. And it's up to you to give yourself the quiz. So it's not optional. That's not what I didn't say it was optional. You have to do it. But I don't want to waste class time on it, so you just have to do it on your own. So I forgot what number we're up to. But anyway, I posted 2 new quizzes. There's a line that pretty much says, oh, quizzes below this, these are mock quizzes, blah, blah, blah. And I tell you how to take the quizzes. So you're going to, one of them is on exponential and logarithms, study all that stuff. And then what you're going to do is you're going to open it, and then you can do it in 15 minutes. Wow. Then you're going to open the answers afterwards, and you're going to grade yourself. And grade it like Jhevon would grade you. Don't be kind to yourself. Don't be like, well, I almost got it right, so I'm going to give myself a point. No. If it's wrong, even if a little negative sign or a little thing that's off, mark it wrong and count up the number of things you got right, and that's going to be the grade on the quiz, because that's how I would have done it. So you definitely want to do that. And yeah, so take the quizzes. So one is on exponentials and logarithms, the other one is on trig. You need to know how to graph in both of these quizzes. Yeah, so with that being said, I kind of just want to move on and not really waste more class time about quizzes, because there are some important things I want to talk about in trigonometry. Now, that being said, I spent a lot of my weekend actually responding to many students freaking out, and I do understand the emotion behind this. You know, 1 week left in class, a lot of people have tests this week, a lot of final papers due, final exams start next week, maybe some people even have some on Friday, I don't even know. So there's a lot of stuff going on, and I understand the feeling of being overwhelmed, and I honestly get it. But that being said, you cannot make a decision based on fear and anxiety and, oh, I'm afraid if I try I'm going to fail, or, oh, I'm so anxious, what if this doesn't go the way I want it to, or, oh my God, I'm going to, you know, there's so much to do and not enough time. You cannot let that allow you to make decisions. You have to get up, come up with a plan, and do what you have to do anyway, despite how you're feeling about it. That is a very important skill to master. Because at the end of the day, everything comes down to habit, right? So why is it that you have to practice a bunch of math problems to get good at math? Or you have to practice anything to get good at it? Because your brain literally rewires itself to get better at doing something that you do over and over and over. This is called habit, right? You are literally designed to do this. Like, as a human being, you have this software in you, just automatically, right? And the differences between people, a lot of times the differences between success and failure, it comes down to habit. It doesn't come down to luck all the time. Like, not, you know, if you're talking about statistically speaking, it's not about luck. It's about what you're doing, the actions you're taking, the decisions you're making all the time. Now, when you start to make those decisions based on some negative emotion that you have, things generally don't work out well for you, and you'll end up giving up on yourself too early. This is not something you want to do. This is not something you ever want to do. And a lot of times we look at these people that we have high respect for, you know. Oh man, I have The Rock on Instagram. He's in the gym every day working hard. I wish I could be like him. Or, you know, there's this person who's just killing it. Every day they're up and they're doing, like, do you think these people aren't human beings like you and like you are? Do you think they wake up every morning super motivated? Do you think they ever not feel like quitting and not feel like doing something? You know how it is that they wake up every day and just go out and kill it? Habit. Habit is how they do it. They almost can't help it. They do it so often, their brain doesn't really know how to do anything else, right? They don't have more motivation than you have. They have different habits from you. The thing about habit, though, is it goes both ways. It will cut you negatively just as much as it will elevate you positively, right? So if you are a lazy bum, right? You're the guy who just sits on the couch all the time watching Netflix. Do you know what? Your brain is going to get super good at sitting on the couch and watching Netflix, right? The moment you decide, I want to do something else, I want to change my life, I want to start going to the gym, I want to start studying more, it's going to be really hard. And it's not because you're stupid or the thing you're working on is really hard. Your brain has a habit of doing something else. It's hard because your brain, you don't have the neural pathways for it. That's why it's hard. It's going to be very hard because you're doing something against your habit. Conversely, if you're someone who's always on top of things, always punctual, always taking care of stuff, always doing what you have to do, always studying, always doing that, then if you don't do that thing, you're going to kind of feel weird. You're going to, I don't know what to do with myself. I got to be doing something. You're just going to get up and start doing something because that's what you're used to. It comes down to habit, right? Every time you want to get somewhere, you need to go through those steps that I laid out in the first section of, like, this was way back, at the beginning of the semester, where I was telling you, okay, choose a goal, make it specific, decide why that goal is important, make sure you know how to assess yourself, come up with a plan, execute it, assess yourself. Are you getting the results you want? No. Start over, come up with another plan. Put that into effect immediately. Assess yourself, blah, blah, blah. This is how it gets done. And here's the thing, your emotions aren't going to always be with you every step of the way. Sometimes you're going to feel frustrated, you're going to feel like you want to give up. But you have to keep going through the steps anyway, because it is a habit. At the end of the day, it all comes down to habit. And you will face different challenges in your life, and they might all look different to you somehow, but at the end of the day, it's all the same thing. At any given time, at any crossroads you're at, there's only one decision to make. Am I going to give up on myself? That's the only decision there is. It doesn't matter if you're worried about a math class, or you're worried about finishing essays, or you're worried about performing at work, or whatever. At the end of the day, that's the decision. Am I going to keep pushing? And the answer is always yes. You must never give up on yourself, no matter what. You might feel anxious, oh my God, but I'm afraid if I try I'm going to fail. Or I have so much things to do and not enough time. Or this is really hard, I don't think I can do it. It does not matter. Come what may, never give up on yourself. Always make the decision to do what you have to do to get where you want to go. The moment you make that choice, you know what? I'm just going to sit this one out. I'm going to give up. You know what? It becomes easier to make that choice again. And then again. And then again. And before you know it, you now have the habit of giving up. Now, you're just that person who looks at other people accomplishing amazing things and wishing, I wish I was like them. The reason why you're not like them is because you made the wrong decision when it mattered. Now, many of you in this class are freshmen. If you learn to give up now, what is the next 4 years going to look like? What is your adult life going to look like? Start fixing that habit. Start being like, I'm going to show up no matter what, right? Yes, I might fail. I'm going to show up and do my best anyway. So, I know it's a very stressful time, but you can't let your emotions decide for you. You need to stand up and say, I am going to show up. I'm going to do what I have to do. I'm going to do my best. I'm going to see where I need to be, see where I am right now, Make a plan to get from here to there and execute it. It doesn't matter if I don't feel like it. It doesn't matter if I'm scared. It doesn't matter if I'm anxious. See where I want to be. See where I am. Make a plan to get from here to there. Execute it. Always execute. Always be executing. Before you know it, you're going to be that person who's just always doing it. You're just going to be always killing it all of a sudden. You always make the decision to face your problems and overcome them. You're going to get pretty good at solving problems eventually. And you're going to be the person people are going to look at, oh, wow, I wish I was like them. I wish I could just keep going and figure things out. Like, they're on top of it. But they don't see when you are there by yourself and having self-doubts. And when you're there by yourself, when they're sitting on the couch watching Netflix, you're doing math problems, right? You are not giving up. You are doing what you have to do. They don't see the hard work that gets you there. And so people wish that they could be like you. That's what you want to be. But it comes down to making a decision. Every day, it's the same decision. Am I going to give up on myself? Never. Never is the right answer. At least if you want the good life, right? If you want the best kind of life you can, like, I can't tell you what the answer should be, but you want success, you want to get most of the things you want out of life, that's always needs to be the decision, right? Can't be, I'm afraid, so I'm just going to run. That becomes a habit. You'll be running forever. Okay? So, it's crunch time. A lot of stuff to do in this last week, I know, does not matter. Do what you have to do. Do your best. Make up a plan, execute it. We're not giving up. You guys aren't giving up on yourselves. You're not giving up on me. Right? You got it, right? At the very least, Kevin's right. I mean, you show up. You have a chance. Right? You don't show up. That's just as... you have no chance. Right? So, if you can't believe in yourself, like, yeah, I'm going to do it, at least have that idea. Like, if I don't show up, then that's definitely it. Don't give up on yourself. Okay? It's going to be hard in these final weeks. Don't do it. You set that precedence now, it's going to be really hard to get out of it. Okay? We are going to now continue with Trig, and we're going to all be very attentive and very focused, and we're going to learn. And we're not going to be worried about what I have to do today or tomorrow or next week or all the crap we have. We're going to focus on learning what we need to learn right now, becoming experts at it, and we will continue from there. We are going to talk about inverse trig functions. Now, we spoke about inverse functions in general before. So the idea is we had a domain. We had elements over here that some function f brought it to some element over here, which is in the codomain. And what the inverse function does is it takes this guy as the input. So this is the domain for f. That is the codomain for f. There is another function sometimes, not all the time, that takes this as input and gives you back that original output. This function is called f inverse. And the codomain of f is the domain of f inverse, and this is going to be the codomain of f inverse. So it's a function that reverses what you did. So we want to do this with trig functions. Now there's immediately a problem here. Sine and cosine. Don't pass the horizontal line test. And last time I mentioned we need to pass the horizontal line test to be able to have a chance of having an inverse. Right? So if you look at the sine function, remember it looks like this, it goes on forever. This is y equals sine. And a very similar thing will happen with cosine. You draw a horizontal line, not only will you touch it once or twice, but an infinite number of times. It fails the horizontal line test in a spectacular fashion. So here's what we do. restrict the domain. We're going to slice off a piece of the sine function that will pass the horizontal line test. So here was y equals sine of x, doing its thing. And here's what we're going to do. We're going to take this part of the function, here where it hits its peak, which is at 1, and here where it hits its smallest value, which is at -1, and we're just going to focus on this part of the function. And we're essentially going to throw everything else away. Right? So when it comes to inverting the sine function, we can't do it in its entirety. What I do is I ignore every part of the graph except this part. It will pass both the horizontal and the vertical line test. So it is a bona fide function, and it will have this behavior between -π/2 and π/2. And so basically what we want to do is we want to just invert that little part. And so you can imagine the line y equals x, and you're just going to flip that on the other side. And then we obtain the graph of the sine inverse function. That's the notation. I'll make some comments about the notation later. But ultimately, what you're going to realize happens here is that your graph, if you reflect this over that line, it's actually going to look like this. Notice that here. Now, what are these numbers going to be? Well, remember, when you're doing the inverse, the x and y switch places. So the π/2 and -π/2 were on the x-axis, and these guys are now on the y-axis. And the 1 and -1 were on the y-axis here. These are going to be on the x-axis over here. This is the graph of sine inverse. So this is sine inverse. Sometimes you also call it arc sine. Now, this is the notation for it, but sometimes students mix this up. Sine inverse of x, it does not mean 1 over sine x. Right? We're used to thinking of the -1 power to mean 1 over, but in this instance, that's not what it means. This is actually just like the f inverse notation. But a lot of people don't like that for this reason, because it doesn't coincide with our normal notation. So they come up with another notation called arc sine, but these both mean the same thing. Just know that this does not mean that. This is in fact what we call the cosecant, but the sine inverse and the cosecant, they're very different. We actually sketched the cosecant last time. One thing you want to know is that the domain of the sine inverse is -1 to 1, and the range of the sine inverse is -π/2 to π/2. And let me just reiterate that the sine inverse function will always output values between π/2 and -π/2 all the time. The sine inverse function works in quadrants 1 and 4, where -π/2 is here, measured it that way, and π/2 is here, measured that way. So it'll output positive values when you're in the first quadrant, because all students take calculus. It will output negative values when you're in the fourth quadrant. Right? So your sine inverse works over here, and not in general, because we kind of had to slice it off to get the inverse function to work. Similarly for cosine. If we look at y equals cosine of x, so that graph look like this, going on forever, doing its thing. The part of the cosine graph that we cut off is actually the part here between 0 and pi. This is the part that we take for the cosine. That section of the graph will pass both the horizontal and vertical line test. I will be able to actually reflect it. So we're going to flip this over and you will obtain this graph. Again, the notation is cosine inverse, but some people like writing arc cosine. So that they don't confuse themselves. And this graph is going to look like the following. So notice that on the x-axis you go from 0 to pi, so it means that on the y-axis you're going to go from 0 to pi. And notice that on the y-axis, notice that on the x-axis we're 0 to pi, so on the y-axis we're 0 to pi. Notice also that on the y-axis we're from -1 to 1. So here on the x-axis we're going to go from -1 to 1. So the entire graph is going to happen inside this box. Notice that here we hit -1 comma pi. So we are going to hit pi comma -1. And over here we hit 0 comma 1. So over here we're going to hit 1 comma 0. And if you flip that graph over, it's going to look like this. Also, we can go on with these values. The domain of the cosine inverse graph, well, again, it's -1 to 1. And the range of the cosine inverse graph is 0 to pi, i.e. Cosine inverse always outputs values between 0 and pi, which means if you're looking at cosine inverse, that guy is going to work in quadrants 1 and 2, between 0 and pi. So it'll output positive values when you're in the first quadrant, it'll output negative values when you're in the second quadrant, because the cosine outputs negative values there. So we definitely want pieces where we can get positive as well as negative values. Another important idea. So we know that to say y equals sine of x, we realize that here x represents an angle, right? So that would be like on a unit circle. Let's put theta so you don't mix up the coordinates. Theta represents an angle, right? So theta is going to be there. And the y represents a real number. It's going to be a number between -1 and 1, but it's just a number. So this basically means that if you're looking at the sine inverse of something, the result itself is going to be an angle. So you can plug numbers in here. And the output will be an angle. So when you're looking for the inverse trig function, you're actually looking for an angle that would have given you this output. Now, how you can know that is just by solving in this particular way. Let's not do that. Let's just actually apply this idea. I'll just jump into some examples here. After trig, let's talk about the tangent inverse after tangent. Then we'll just jump into some examples of how we're actually going to use this tangent inverse. Similarly. So, the tangent graph, we also saw that last time. This guy had asymptotes at every odd multiple of pi over 2. So, pi over 2, 3 pi over 2, 5 pi over 2, etc. Minus pi over 2, minus 3 pi over 2, minus 5 pi over 2, etc. And the graphs looks like that. Now for this one, obviously that doesn't pass the horizontal line test. We just take the middle one. So look at this guy here. So this right here. We ignore all the other branches, and we're going to just reflect in the line y equals x. And ultimately that leads you to this graph, y equals tan inverse, might call arctan. We couldn't touch pi over 2 and minus pi over 2 on the x, which means we can't touch now pi over 2 and minus pi over 2 on the y. X and y switch places. And if you just flip this graph, it'll actually look like this. It went forever on the y, it's now going to go forever on the x. They'll actually always approach minus pi over 2 going that way, always approach positive pi over 2 going that way. You want to find the inverse tangent. So the domain of tan inverse. Domain is actually all real numbers. You can actually evaluate this at any x value. The range of inverse tangent. Well, that actually, not including minus pi over 2 and pi over 2, it'll hit all numbers in between. I.e., your tangent inverse, it will always output a value strictly between pi over 2 and minus pi over 2. That's going to be important to know in calculus. But that guy, as you will see, he works again in the first and second quadrant, first and fourth quadrant, but you're not allowed to actually touch the edge. So from pi over 2 all the way down to minus pi over 2, everything except those two values. Your tangent will give you positive values in the first quadrant, it will give you its negative values in the fourth quadrant. Again, because of all students take calculus. Now, the other trig functions are dealt with similarly, but we're not going to do them, and you're very rarely ever going to see them actually. So we're not. The other trig functions. So how about secant, cosecant, cotangent are dealt with similarly. You don't need to know them. At least not for this class, and it's very rare that you'll need to know them for future classes. Especially the graph of tangent inverse, that's definitely something you're going to want to know, because that is going to come back and you will be tested on that and you're expected to know that. The graph of sine inverse and cosine inverse, it's very good if you know, but you can almost survive if you don't know it. If you ever have to know it, I just showed you how we figured it out, so you can just construct it from that. But the graph of tan inverse, it's something that you should know like by heart. Like now in your mind, that's just like y equals x squared. You don't have to figure out what that looks like. You just know what it looks like. This is a very important graph for now and the future. Okay. So those are the graphs. We're not going to have to draw like transformed versions of these, but you do have to know how to do calculations with inverse functions. So to that end, all you have to do is just remember that the inverse function, the output is the angle. And once you know that, you can actually figure things out based on what I've already told you. So let's actually just do some of these. I have a lot of examples here. I don't even know if I want to do all of them. Sine inverse of 1. Sine inverse of negative 1. A lot of them would be quick, I guess. Cosine inverse of 2. Tan inverse of 1. Tan inverse of 0. Cosine inverse of minus a half. Tan inverse of minus radical 3 over 3. Okay, tangent of tan inverse of 5. Sine of sine inverse of minus 3 over 4. Cosine of sine inverse of x. Here I want you to simplify. So we're just going to compute a bunch of inverse tangents. Similar to how we can just compute the trig functions at certain values, we want to be able to compute the inverse functions at certain values. Now, this is pretty much just an exercise of how well you know all students take calculus, computing reference angles, as well as the table of values that I gave you before for the angles in between 0 and 90, the 30, 45 degrees, 60. So, let's do A. Sine inverse of 1. How do you do that? So here's how you want to think about it. Maybe I'll just mention that. If you want to set this equal to something, you would set it equal to some angle. So the question you should be asking yourself is, what angle theta do I need to have so that the sine of theta is going to give me 1 as the output, right? So remember, the sine inverse is going to take the output of the sine function and give you back the original input. So now you just want to think of, what angle do I need in order to get a 1 as the output of a sine function? And what's the angle? Sine of what gives you 1? 2? Yeah, that's it. So it's kind of like you have to know that table backwards. Whereas I'm going to give you a value inside the table, and you have to figure out, one, what original angle came from. One thing you have to make sure is that this is in the range minus pi over 2 to pi over 2. So where's it? That's the 1. If you come up with an answer that's not in that interval, you have to find the reference angle for that answer in that interval. That's basically what you have to make sure. Because the sine inverse will always alphabetize between here and here. That's very important. Okay. Now, some of the rest of these should be pretty quick. Sine inverse of -1. What do you plug into sine to get -1? Minus pi over 2. See? Cosine inverse of 2. What do you plug into cosine in order to have an output of 2? Undefined. That's right. It's like, error. Yeah, cosine will never output 2. The maximum it outputs is 1, right? You know the cosine well enough, you know that much. You know that it'll never be a value higher than 1. So that's actually undefined. What about the tan inverse of 1? What angle do I need to plug into tangent in order to have 1 as the output? 45. Higher than 4. Why is that? Because remember, tangent theta is equal to the sine of theta over the cosine of theta, which means in order for this to output 1, the sine and the cosine must give me the same value. When does that happen? If you remember the table, that happens at pi over 4. Sine and cosine both give you radical 2 over 2. So if I divide both of them, I'll get 1 as the output. When does that happen? At the angle pi over 4. That's why that's the answer. So this is one of those things, it's going to be confusing if you don't have all the stuff memorized that you should have memorized. If you have it all memorized, it's going to, yeah, like obviously. E, tan inverse of 0. What angle do I need to plug into tangent in order to get 0? In other words, notice that what I'm asking you is where's the sine 0?
0.
At 0.
Would it be wrong if you did, if you said at pi, 2 pi?
Right, so now you could say, oh, well, sine is also 0 at pi. But why is that the wrong answer? Because remember, your tangent is always between minus pi over 2 and pi over 2. Pi is not in that window. So even though pi is an answer in general, yeah, sine of pi will give you 0, your inverse trig function doesn't stretch that far. Your inverse trig function can output as large as pi over 2 or as small as minus pi over 2. It will not output anything outside that window. So you need to find a value that makes sine 0 inside that window. 0 is the only value inside that window where the tangent will be 0. So that's why 0 would be the correct answer and not pi or 2 pi, etc. Because you must be in this window. Right? That's always a consideration. So our inverse functions, remember, they're not a fully fledged out trig function. We just slice off a part of that trig function, so it doesn't apply broadly. It only applies in certain windows. So tan inverse of 0 is 0. Okay. Cosine inverse of minus a half. What do I need to plug into cosine to get minus 1/2? So here's what my thought process would be. So I want cosine inverse of minus 1/2 is some theta. This means I want cosine of theta to give me minus a half. The question I would ask myself is, where does cosine theta equal positive a half? Why do I care about positive a half? Because I can just use a reference angle to figure out minus a half. Right? So there is some angle in the first quadrant where the cosine of this angle is going to give me positive a half. Now where does that actually occur? In the table, where does cosine equal 1/2? Right, remember the cosine goes 3, 2, 1. So pi over 3 is the angle that this would happen. But you don't want that, you actually want the reference angle for that in which quadrant? Well, this one. right? Because remember your inverse cosine works between 0 and pi. So you want the equivalent of that angle in the second quadrant. Now what is that? Well, that's going to be 2 pi over 3. Right? Because that's 1 pi over 3, 2 pi over 3. Just like count off the slices. And so this is going to be 2 pi over 3. So usually when you get a negative answer, first figure out what's going on for the positive answer. You'll get something in the first quadrant. Now, if you don't want a positive value, like in the first quadrant, you actually have to figure out what's the reference angle for that in a quadrant that I want. So, if you're looking at a cosine inverse and it's negative, you need to figure out who in the second quadrant is going to give me that answer. If you have a sine inverse and it's negative, you have to figure out who in the fourth quadrant is going to give me that answer. Or, a little bit easier, figure out who in the first quadrant gives you that answer, and the negative of that will give you the second answer, because sine has that nice property of being odd. So that one is going to be 2 pi over 3. Okay, do this one quickly. Tan inverse of minus radical 3 over 3. Tell me when you have an answer.
Like you said,
Yeah, you have an answer? What's your answer?
my final negative pi over 3.
Okay, explain.
Well, because first tangent needs to be in the fourth quadrant.
Right, it's negative, so which means I should be in the fourth quadrant, which means the answer needs to be somewhere between 0 and minus pi over 2. How did you come up with minus pi over 3?
Because with cosine over cosine of 60 degrees, you get pi over 3. I mean, 3 over 3.
Because you know the table so well that you realize, oh, the sine of pi over 3, that's going to give me radical 3 over 2. The cosine of pi over 3, that's going to give me 1 over 2. So what does that actually give you?
Oh, wrong one.
That's the wrong one. Notice that this would give you radical 3.
So
That would be the answer for, just if I had negative radical 3.
pi over 6.
However, if you look at the other one, pi over 6, sine of pi over 6 is 1/2. Cosine of pi over 6 is radical 3 over 2. Notice that that simplifies to 1 over radical 3, which you can rationalize by multiplying and dividing by radical 3. So you get this one. And so you realize pi over 6 gets you the positive value. So pi over 6 here, pi over 6, that gives you the positive radical 3 over 3. That's the tangent. And so to get the negative version, I just want to find the reference angle for this in the negative part, and that's just negative pi over 6. So this ends up being not the right one. Well, you knew the answer wasn't pi over 4, so because that would give you 1. But if you tried pi over 3, you'd realize I get that. If I tried pi over 6, I get that. That's the one I want. Now with practice, you'll know how to pick the first one in the first place, right? So here you'd realize that this here is just 1 over radical 3. So I need the cosine to be giving me a radical 3 and the sine to give me a 1. That happens at pi over 6. Where each of them is divided by 2, but the 2 ends up canceling. So this is actually minus pi over 6. Now this one, it'll remind you a lot about how functions actually work. You know that if you take f of f inverse of x, you just get x. So this one is just actually going to be that. Right? But there is a caveat when it comes to trig functions. So the inverse can only work in a certain range, so remember. Trig inverses output a certain range. So if f is a trig function, one thing you might have to look out for, and I don't know if one of these examples are like that, then your f of f inverse of x equals x. The guy that's out here may be a reference angle to the guy that's in here. It might not be the exact angle. All you have to do is know where the trig functions work, and you find the right angle. So if you're looking for, let's say something here is outside of a window, let's say your f is like a sine or something, and the x in here is outside of the window between pi over 2 and minus pi over 2, you have to choose the output here that's inside the window. Well, that one's going to be, it works the other way around. But you just have to be aware that the trig functions, the inverse functions, don't work everywhere. So you always have to be kind of worried about, is this really the answer I want, or do I want some reference angle of that answer? But this one is actually fine because the inverse tangent actually works everywhere, right? So in here I can have whatever domain I want, and the tangent also goes from negative infinity to positive infinity. So this guy can take any input he wants because it goes from, his domain is minus infinity to positive infinity. This guy can output any number he wants because his range is from negative infinity to positive infinity. So they kind of just end up canceling as expected. If you have sines and cosines, though, you kind of have to worry about other things. Not here, however. So these two here, they're going to use a special technique, which you're going to need now and in the future. You see something like this, 3 over 4. That's a very weird number, but we actually can figure out what that number is. So first of all, if you look at sine inverse of 3 over 4, minus 3 over 4, what you will notice that is if I set this equal to theta, this means I want my sine of theta to equal minus 3 over 4. Now what that actually means is there is some right triangle where the opposite is 3 and the hypotenuse is 4 that is going to have my sine function working that way. This side would be what? Pythagoras' theorem. So it's going to be the square root of this squared minus that squared, so that's 16 squared minus 9. That 4 squared, which is 16, minus 3 squared, which is 9. 16 minus 9? It's radical 7. So now, if I look at the sine of sine inverse of minus 3 over 4, this is negative, so we're going to keep the negative. This is the same as the sine of theta quickly here what we actually want because I know how the sine inverse behaves. The fact that it has a negative number tells me that it's in the fourth quadrant. So technically I should have drawn the triangle this way, but I don't, it doesn't actually matter. But if you wanted to be very pedantic, that would be the length 3, this would be the length 4, that would be the length radical 7. What you'll notice is that the 3 is negative, so you should really have a negative sign attached here. And so when you take the sine of this angle, it's like you have negative 3 over negative 4, opposite over hypotenuse. Sine inverse of this is that, is theta. So here, if I plug in theta here, my sine is going to be what? Negative 3 over 4. And is that in the right window? Is that between minus pi over 2 and pi over 2? Yes. So this is between minus pi over 2 and pi over 2. So it's fine. But you always have to worry about that. So in this case, they do actually just cancel each other. But this idea that I just showed you here, just constructing a triangle, is super important when you're plugging in inverse trig functions into each other. There are going to be a lot of rules that you derive in calculus that's based on that fact. It's possible that you can take an inverse trig function, plug into another trig function, and the result is something that doesn't have any trig functions in it. How you would do that is you would set the sine inverse of x equal to theta. This would mean sine of theta equals x. You think of x as x over 1, which you think of as opposite over hypotenuse. This means that you can set up a triangle where the opposite side is x, the hypotenuse is 1, which means this side is going to be the square root of 1 minus x squared, which means the cosine of the sine inverse of x, well, that's just the cosine of theta, because my sine inverse of x is theta. And if I wanted to do cosine of theta, I can use the triangle. This is just going to be adjacent over hypotenuse. So that means the cosine of sine inverse of x is going to be square root of 1 minus x squared. So I can actually write this without trig functions. So in Calc 1 you're going to derive something called the derivative of sine inverse, and you're actually going to use this fact to figure it out. So that's all you need to that's all you need to know about inverse trig functions. Know their graphs, know how to compute their values. That's pretty much it. And you only need to know the sine, the cosine, and the arctan, the sine inverse, the cosine inverse, the tan inverse, especially the tan inverse, but know the others as well. And then pretty much know how to compute them. And at the end of the day, it really comes down to you really having memorized the stuff that we did last class. Like when that stuff is burned into your brain, this stuff is going to be very easy. Otherwise, it's kind of going to be confusing. You're like, what did you just do? What did you just do? Like if you're asking yourself that question, it means you haven't memorized the stuff from last time. So memorize the table, memorize the graphs of the trig functions, memorize the reference angle idea, memorize all student state calculus, know how these all work together. Once you have that down, this is not going to be a problem at all. Right, you're just kind of going backwards. So it's like before where you looked at the value outside the table. So this was pi over 6, that was pi over 4, this is pi over 3. Meaning that sine theta, this is cosine theta. Do you guys remember how we fill this up? What do you do across the top? 1, 2, 3, 3, 2, 1, square root everybody, divide everyone by 2. Right? You need to know how to fill out that table and know how to just visualize it in your head. Now, when you're looking for just the sine of some angle, let's say the sine of pi over 4, it means someone gave you something that's in the heading of the table, and you need to find the corresponding thing inside the table. So that's going to be radical 3 over 2. But if someone asks you, what is the sine inverse of radical 2 over 2, it's the opposite. They're actually giving you what's inside the table. And you have to figure out what heading did that come from, right? So knowing one, you kind of automatically know the other one. So if you're having trouble thinking of that, what it really means is you have trouble thinking of this. And the only way you should have trouble thinking of this is if you haven't memorized it, right? So you memorize it, and you're just going backwards. So if you ask me about sine of pi over 4, it's radical 2 over 2. That means the sine inverse of radical 2 over 2 is pi over 4, right? You just go backwards. So instead of going from here to there, you're now going from here to there. Now, in the few remaining minutes we have left, I guess I'll just introduce some formulas that we're going to use next time. Consider this. It's going to come out of nowhere. Like, math people love doing that. Consider it. They give you some random thing. Right? I don't. Okay. Suppose I'm stacking two right triangles on top of each other. So here's a right triangle, and then I stack on top of that another right triangle. Why would you do that? Just go with me here. Okay? Just 'cause, yes. I could actually create a rectangle from this. And here's what we're going to do. I am going to call this angle, let's call it big A, and call that angle, let's call that big B. And I'm constructing these so that the hypotenuse of that triangle is 1, but otherwise I don't tell you anything. Here's one thing you would notice. Remember the sum of angles in a triangle add up to 180? So if you have a 90-degree angle plus B, the remaining angle is going to be, I don't know, what's it called that? You don't really need to know this. Alpha. Or we're just going to figure out. So if you're in a triangle, one is B, whatever that angle is, one is 90, the other must be alpha, and vice versa. If one is 90, the other is alpha, the other one must be B. Using that idea, you could actually figure out what this angle is here. Because we also know that the sum of the angles on one side of a line should also add up to 180. Which means this angle plus 90 plus alpha should all add up to 180. But I know if I'm adding alpha and 90 to get to 180, I need to add B, which means this angle is also B. So you can figure out what that angle is. Okay. What's the point? We're getting there. Okay. Let's label these. U, V, W, X, Y, Z. Now, here's something that we learned last time. And we did this by putting this inside a big circle of radius r using similar triangles. If you have something like that, and this is say theta, then the height of the right triangle is given by the y value, which is y, and we know that y is equal to r sine theta. And we also know that the x value is given by r cosine theta. So if I know the hypotenuse of a triangle and I know an angle, I can also tell you the lengths of the other sides in terms of the trig functions. Let's use this repeatedly. We can figure out the lengths. So let's go back to this, and we're going to derive some really cool things now. So, boom, boom, boom. This is B, this is A, this is B. Okay, if this is 1, then using this idea, imagining this right triangle here, this length must be 1 times the sine of A. This length here must be 1 times the cosine of A. Okay. Now, looking at this triangle here, this I'm going to look at like my r. So this side must be r times the sine of b. But r is cosine. So here this is cosine A times sine of b. And that's the length from here to here. Similarly, this side is going to be r times the sine of b. R times the cosine of b, right? So this length here is going to be cosine A times cosine of b. Similarly, I can figure out this one. Okay, so if my r is sine, this must be r times the cosine of b. So this here is sine A cosine b. Figuring out this length, this must be r times the sine of b. So that's sine of A sine of b. This length here is going to be what? And this length here. Notice that this length here is equal to this length here. And if I imagine this as the big triangle there, the angle here is A plus B. That length here is going to be sine of A plus B. And if I look at this length here, that then, again by that idea, that is going to be the cosine of A plus B. So this length is the cosine of A plus B. So I'm pretty much just using this idea over and over, and I can actually fill in all these lengths. Now here's something cool. You want to look at the sine of A plus B. And the cosine of A plus B. Here's what you'll notice. The sine of A plus B is actually just adding these two lengths together. Right? It's this plus that. And if I take the cosine of A plus B, I can think of that as this length minus that length. These guys are called the addition formulas. important. We're going to use them to figure out a lot of stuff. We'll stop there. Remember, don't give up. It's time to push harder.